In this example, let's consider a locomotive or train that's pulling 15 cars behind it. I want to calculate the ratio of the force between cars 3 and 4 and the force between cars 7 and 8. Each car has a mass m, and the locomotive is moving forward with some acceleration, let's say 6 meters per second squared. So the question essentially is, how hard does car 3 have to pull on car 4? And remembering that by Newton's third law, also the reaction force of 4 on 3, compared to how hard car 7 has to pull on car 8. To begin, let's think about the isolated experience of the locomotive. The locomotive is attached to car 1. Moreover, while it is clearly pulling all the cars behind it, its immediate experience is limited to the fact that it's attached to car 1. Extending that concept to the last car, we can see that car 14 is attached to car 15. The fact that car 15's acceleration is equivalent to that of our system, 6 meters per second squared, suggests that 14 must be pulling on 15. Since we know that 15 is accelerating and that its mass m is identical to that of the other cars, then the force that 14 exerts on 15 to pull it forward is ma. Now let's do that again for car 13. Car 13 is pulling car 14 forward, but since 14 is attached to 15, car 13 is also pulling forward the mass of 15. So from the perspective of car 13, it is essentially pulling forward one big car of mass 2m. Thus the force between 13 and 14 is that big mass 2m times acceleration, remembering that everything is accelerating at 6 meters per second squared. We could continue this pattern for each car in the train, but the original prompt requires us to evaluate two forces in particular. First, car 3 and 4. In answering the question for 13, we looked at it and determined that 13 must pull the mass of both of the two cars behind it. So to determine the force between 3 and 4, we can look at car 3 and think about how many cars are behind it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So car 3 is going to apply a force on car 4 that can accelerate 12 of those masses at 6 meters per second squared. So this would be 12 masses of cars times 6 meters per second squared. What about the force between cars 7 and 8? According to the same reasoning as before, car 7 pulls on car 8, which is in turn pulling on all the masses behind it. And there are 1, 2, 3, 4, 5, 6, 7, 8 cars behind 7. So that would be pulling forward 8 masses in an acceleration of 6 meters per second squared. The ratio of the two forces in question then equals 12m times 6 meters per second squared over 8m times 6 meters per second squared. The acceleration and mass cancels out, leaving us with 12 over 8, or a ratio equal to 1.5.